So let's talk about the two-time pad. This thing here, this is the perfect cipher. Been known for centuries. This is the perfect encryption system. If you want to encrypt something, what you do is you have a lot of key. You just have page after page of random letters on a pad that you give both parties have a copy of this, and then you encrypt every letter of your message using one letter from the pad. You could use anything like, for example, the Caesar cipher. You could just use that letter. If it's A, don't move it at all. If it's B, move it forward one letter in the alphabet. If it's C, move it forward two letters in the alphabet. But you use each letter in the key just once, and you never reuse it at all. You cross off the lines as you use them, and you go on to the next page for the next message. And there is no pattern at all in the key stream. This means any message will just turn into random letters, and if you tried to decrypt it without knowing the key, you could try every possible one-time pad, and you would create every possible message of that length. So you'd see every possible message, and you'd have no way to tell which one is correct. So this is, as far as anybody can tell, a perfect unbreakable system. The only problem is a key distribution system. You have to deliver enough key to the other person you're sending a message to, so they never have to reuse any of the key. So you'd have to give them like a whole book full of keys, and then you send only that many messages, and then you have to give them more keys. So the key distribution problem is very large. And that's why this system is almost never used in practice, because the key distribution is such a problem. However, the military did use it in World War II, and what happened is the Russians used it. And the Russians ran out of keys. So what they did was the way they made the keys is they would type random letters in a typewriter and have carbon paper, one for the sender and one for the receiver. But they put in more layers of carbon paper and made like 4 and 5 copies of the same key stream in order to make keys faster. And it turns out that this system shatters like glass. This is fairly common in cryptography. You have a good system, but when you make one little mistake, the security is destroyed. And that's why they call this the two-time pad. It's written up in this book, In the Enemy's House, how this really happened to the Russians in time of war. Because they reused the keypad, the system can be cracked. And it's very easy to crack it, and you can see it with some simple Python scripts. So I've got those here. And you can run Python on any operating system. If you've got Linux or the Mac, you've already got Python. If you have a PC, you can install Python quite easily. So here, for example, let me just clear this. All right. So here is a one-time pad. Now here, what I'm using is a version of the one-time pad that is not the most secure, but it's the easiest to understand, where I use a key that is in fact a sentence. Now, it would be better if the key was just random letters. But anyway, here I use this for the key, and here's my plaintext 4 and there is no particular limitation on the length of the plaintext. It just has to be shorter than the key. So now all I do is loop through the plaintext, and in this case I'm doing XOR with the key and then printing it out. So if I run this Python, any way to combine a character of key with a character of the message is fine. Here I used XOR for the ASCII values. So if I run this OTP1, then here it is. The F is a 46 in hex. Here's the key, unbreakable, awesome. Here's the message, 7. So the F is the plaintext, the U is the key, and when you XOR them, you get a binary 13. The little o and little n, since those are adjacent in the alphabet, N, O, they only differ by 1, so the XOR gives you a 1. And so this encrypts it as a series of hexagonal bytes, and there they are. So the encrypted message is just that mess of hexadecimal code. And you can reverse it. If I look at the reverse is here as OTP2. The only complicated part of that is that your ciphertext has to be recovered from hex values, and in Python you do it this way, bytes from hex. And then you do the same thing, character by character. You do XOR again to get it back. So if you run this one, that recovers the original message, taking the hexadecimal value of the encrypted ciphertext and XORing it with a character from the key, and here you see BREA key, unbreakable, secure. This is the same key, and you recover the letters one by one. So that is the one-time pad acting as expected. And you've got a couple of flags to find here, just showing you can implement the one-time pad by making a modification of that script. Now, then we get into the crib drag. This is how you break it. So if you have two ciphertexts that are encrypted with the same key, then what you do is you guess some part of the answer. You have to be able to guess a word or two, and you can try it anywhere. So you might imagine that the word "the" will appear somewhere. Perhaps the first word is the word "the." If you don't find success there, you just try moving the word "the" out of every position until you find a position that works. And what will happen is, if you guess the word "the," and the word "the" appears in either message or the key, then the rest of it will turn into clear text. So here, the key actually starts with "the," so both of the messages became readable. This is NEV and this is YOU, and the fact that the first letter is capital and none of the other letters are capital strongly suggests that I have successfully guessed the key. Since I have the first few letters of the key, what you do is you guess a few more letters what would continue this. Like after the word "the," there might be a space, or there might be a word like "these" or "there." This NEV, maybe the next two are ER, maybe that's never. This U, maybe there's a space here. So once you have a few letters that are clear, you guess the next letter and then implement it and see if something else becomes clear. And you just jump back and forth, filling a word or two here and there until you have solved the problem. That turns out to be extremely effective. You don't even need a computer to do it, and it shatters the whole system like glass. So I've got a couple of those set up here. If I look at my crib one, all right, what this does, I implemented something here where I just take the plain text coming in, and that's these two, and then I wrote a loop so it'll calculate. You have the key, and you have the ciphertext 1 and the ciphertext 2, and I just filled in with dots all the unknown parts of the key. And so you can guess any character, and it will just recalculate everything and print them out in a loop. This is an interactive way to do it, and a very good idea. Python 3, crib 1. All right, so now I have "the" and "never." So if I put a space in the key, if I guess K, and location 3 is a space, then "the" now has a space, and this NE grew an E, so I can guess R. So plain text 1, location 4 is an R. All right. And here I've got the Q. I don't know what that is. So here, U apostrophe L. The next letter is obviously an L and then a space. So plain text 2, location 5 is another L. And I can tell that's working because I have a QU. So this is turning. Then the next, after that, would be a space. So plain text 2, location 6 should be a space. And so now you see how it's working. Things are becoming clear. So once any part of it is true, you can just guess words around it and walk your way through it and gain the key and the plain text. So it's good, clean fun. And so once you get some system like that working, you can solve this one and that one and that one. There are more and more harder ones to solve. I found this very charming. It is amazing how the most perfect system that has ever been invented is completely destroyed by the simple mistake of using the same key more than once.